Okay, we are going to balance this equation right now. This is an interesting equation because it involves this chemical, NH3, which is known as ammonia. Ammonia is a very common chemical. It has a tetrahedral form, but you can't see the one on top because that's a pair of electrons that's not bonded. Okay, ammonia was named after a temple in Libya. That's an interesting story. I'll tell you about that if you want to know. It was named after a god, Jupiter Ammon. That's where ammonia comes from. Not to be confused with ammonium. Ammonium is NH4 positive. This is a polyatomic ion, whereas that is a molecule. Ammonia, ammonium. The only difference is the ending. And if you have household ammonia, which is a cleaner, well, in solution, ammonia always generates some ammonium. So you actually do have some in there. All right. We're taking that and we're reacting it with oxygen. Remember, O2 is just called oxygen. And if you have a reaction with oxygen, well, that's a dead giveaway. Which type of reaction is it? Which reaction type? There's one category of reaction that is a reaction with oxygen always. Very easy to identify. And that is combustion. Combustion, you're reacting a chemical with oxygen, making a compound with oxygen. But a better way to look at it for this reaction is this way, okay? Because what we're really reacting is a compound reacting with oxygen, producing two chemicals that both contain oxygen. This is another way of showing the combustion generic pattern. So any reaction with oxygen is always combustion. Okay, so that's good. And then what are we producing? The products, which is this side, this produces these. The yield sign shows you where the products start. Most famous chemical formula in the world, H2O, H2O. Okay, organic chemists write it HOH. This is, of course, water. Okay, water is a very common product. Maybe that's why we have water everywhere covering the earth. It's a very common product. The other product here isn't quite so common, not quite as good. This is NO, nitric oxide. This is an oxide of nitrogen. Oxides of nitrogen form when there's a reaction, well, this can make them, or if you get a reaction between nitrogen and oxygen, which isn't too likely in the atmosphere, but it can happen under certain conditions. Oxygen is a clear gas, we breathe it. Nitrogen is a clear gas, we breathe it. We breathe these, that's fine. But we don't want to breathe these, okay? NO, N2O, and NO2, oxides of nitrogen. Okay, this one makes you laugh, this one makes you cry, this one makes you die. So we would not really do this reaction in our lab. In fact, when this reaction happens, in like an industrial site, a lot of times they have to clear out the town, evacuate the town because of these products. They can be really toxic, really hazardous. Now, the great thing about this reaction though isn't that we're going to do it in our lab and do the experiment, it's that it's really good to balance because we must obey this law. And this is breaking the law of chemistry, the conservation of mass. Right here, it's just breaking the law. Why? Because nitrogen's fine. Okay, even oxygen is fine, but hydrogen is not. Remember, you can figure out either looking at these models how many are present or looking at the chemical formula. Remember that everything that's not written is an invisible one. So imagine that's a 1, that's a 1. Anytime you don't see a number, imagine that it's actually an invisible 1 that's there, okay? So we've got 1 nitrogen, okay? 1 nitrogen. We've got 2 oxygen here, and we've got 1 oxygen, 1 oxygen. That's 2 on this side. 2 and 2, that's fine. Hydrogen is the problem. For hydrogen, notice there's 3 on this side, 1, 2, 3, and there's only 2 on this side, 1, 2. So if you have 3 on one side and 2 on another, what does that remind you of? What's the problem here? What's the way to fix this? That's one of the techniques for balancing equations. It's odd even. So when you have odd even situation, It doesn't matter which one is more, you got to make the odd side even. So to make the odd side even, we usually just double it, put a 2 right there, and now that means 2 ammonia molecules. That's what that 2 means. 2 times this. Okay, wait a second, I just threw off the nitrogen. Better fix that right away. I'll put a 2 here now, coefficient of 2 in front of the nitric oxide, and now we fix the nitrogen. And the reason we did this was to balance the hydrogen, and now we can. Because there was no way to make this an odd number, so we had to make this even. But now we have 6, which is an even number. So if you've got 6 hydrogen here, 2 times 3, 1, 2, 3, 4, 5, 6, I can get 6 here. What do I need to multiply the water by? How many of these do I need? How many of these? What's the coefficient? I need a 3. I need a 3 right there. And that, of course, means 2, 3 water molecules. I'll try to show them separately. They're not all merged together, but I might have to put them a little tight here for space. But they're separate water molecules. It's just that we have 3 of them. That's why it multiplies by the whole chemical. The coefficient multiplies by the whole chemical. Okay, so now we've got 6 hydrogen, 2 nitrogen, 2 nitrogen. Now it's time to fix the oxygen. The reason we do the oxygen last is because it is split up on this side. The oxygen is in 2 chemicals. So we always want to deal with those last. So let's see, we have 3 oxygen here and 2 oxygen here. 3 plus 2 is 5 oxygen, and you can see them here, 5 oxygen atoms. Over here we've got 2. 5 and 2. What does that sound like to you? Odd, even. Again, this happens twice in this particular equation. This is why this is such a good example. 5 and 2, well, what do I have to do to fix this? I can never get this to be 5. Whatever I multiply it by, any whole number will never get us to 5. So I got to make this side even first. So you got to make the odd side even though it's got way more oxygen. Doesn't matter. So this isn't making it odd. This is 2. That's fine. It's this. This 3 is making it odd. So I've got to double that. That's the part you double. The part that is making it an odd number, and now it's not an odd number anymore. So now, first of all, what that does is that throws off the hydrogen. So let's just fix that problem right away. How many hydrogen does that make? 6 times 2? Okay. Oh, by the way, so now that I put a 6 there, I better put the water molecules on. Okay, 6 water molecules there. They're all separate ones. I just have to squeeze them close together, so for space, I think that's about the best way I can do it. Okay, 6 water molecules here. That gives me 12 hydrogen. Well, how am I going to get 12 hydrogen over here? Well, what do I have to multiply the 3 by to get 12? I have to multiply it by a 4. So I'm changing this to a 4 now, kind of doubling it. A lot of times when you double one thing, you have to double other things too. So again, notice I have to cram these in here. So now we've got 4 ammonia molecules, which gives me 12 hydrogen. 3, 6, 9, 12 hydrogen. Hydrogen is balanced. Oh wait, look what we just did. We just threw off the nitrogen. So now nitrogen is 4. How can I make this 4 nitrogen? Change this to a 4. Notice why you want to be able to erase your numbers, right? You want to balance with a pencil or with a dry erase marker. 3, 4. Okay, so that's 4 nitric oxides. Maybe I'll set them off like that a little bit so you can see that they're different. And that, of course, gives me 4 nitrogen. 1, 2, 3, 4. 4 times 1. 4 nitrogen. So nitrogen is balanced. Hydrogen is balanced. Oh, we never quite finished the oxygen. We did do the odd-even technique, but we never finished it up. But now let's do that. We've got 2 oxygen on this side, obviously. 2 times 1. 2 oxygen. Okay? We got way more on this side. Okay, 6 times 1 is 6. 4 times 1 is 4. 6 plus 4, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 oxygen atoms. So we got 10 on this side, and we got 2 on this side. Is that odd even? It is not odd even because 10 is an even number as well, so it's no problem. Barely an inconvenience. All we have to do is turn this into 10 oxygen. What coefficient do I need here? What coefficient do I need to make this 10? I need the number 5. 5. And that means, of course, 1, 2, 3, 4, 5 oxygen molecules. Okay, so everything on this side is balanced by everything on this side. This is where the atoms started. This is where they ended up. Before the reaction, after the reaction. Reactants, products. And just to make sure, we've got 2, 4, 6, 8, 10 oxygen, and we already counted 10 over there. Everything's now balanced. I can put a little check. The only time this might be wrong, if you have everything the same on both sides, is if you can divide all the coefficients by 2 or 3. But notice, you can't divide through by 2 because that's an odd number. You can't divide by 3 for sure because only this number is divisible by 3. That's the only time you might be wrong if you think it's balanced on both sides, is if you've doubled the whole thing. Because this would work if you doubled it. So now, we've obeyed the law, conservation of mass. We've got a balanced chemical equation. Okay? This is the combustion of ammonia producing water and nitric oxide. And isn't it funny that the only little tiny difference at the beginning was only one little hydrogen difference? That was the only thing that was off. The smallest atom in the universe, one atom of hydrogen, and yet that led to all this. That's why this is such a great one, because we had to use our techniques, and it involves quite a few changes. So most equations are much easier to balance than this. Many equations don't involve any coefficients, just ones that you don't even change. Some of them might have like a 2 here or a 3 there. This is an unusually hard one. So don't expect most equations to require this much work. So we just obeyed the law of conservation of mass. We did it.